Good evening, everyone. Welcome to the week 3 live interaction session. Let's just wait for a few minutes for others to join before we begin our session for today. Let's start our session for today. I hope I am audible. Let me just share my screen. Is my presentation visible?
Yes.
Okay. So let's begin our session for today. So I welcome you all to the week 3 live interaction session for the course Polymers, Concept, Properties, Uses and Sustainability. So for the first 2 weeks of this course, we have seen more on the general aspects of polymers, their concepts, properties, uses and sustainability, and our week 3 interaction session as well as the course content is also dedicated towards seeing this polymers and their concepts. So last week we saw more on the polymer concepts of like the polymer conformations, where we saw how a single macromolecular chain, the conformation of a single macromolecular chain determine the properties, as well as we also saw some of the fundamental concepts of the single macromolecule. We defined few of the terms like end-to-end vector distance, contour length of a macromolecule, and then we also discussed about the spring bead model, wherein the polymers once stretched will actually come back to its shape. And so there we ended our discussion on the polymer conformations. So this week we have two parts to discuss. So one is basically your biopolymers, structure of biopolymers, and then the other one is the states of polymers. So more on the uh, amorphous and the crystalline states of the polymers and their kinetics of this crystallization. So speaking of the first part, that is your structure of biopolymers. So biopolymers, as you know, as everybody know here, there are many different examples starting from cellulose, hemicellulose, pectin, lignin, DNA, RNA, proteins, and the list goes on. So specifically the DNA is of particular interest because of its complex structures. So they basically exhibit four different types of or four different levels of structures, such as primary structures, secondary structures, tertiary structure, and quaternary structure. What is more important to see in this case is basically that these proteins as well as this DNA molecules, the majority of their interactions are basically hydrogen bonding, which mediate these specific interactions. So in all these kind of biopolymer systems, if you see, the hydrogen bonding plays a very important role. So people often use these, or use these ways of hydrogen bonding to manipulate the polymers, even at the laboratory scale or with the synthetic polymers. We try to use this hydrogen bonding to make systems of our particular interest. Specifically, this hydrogen bonding plays a very key role in self-healing materials. Like if you just cut a material into two parts, and once you basically join them, they heal on its own. So there, this hydrogen bonding plays a very important role, and this concept of hydrogen bonding actually comes from these biological systems. So the next one that was discussed in the course is about the casein milk protein. So the casein is one of the very good examples of a protein which is found in the milk. So there are totally four different varieties of alpha 1, alpha 2, beta and kappa casein forms. So these caseins contains both hydrophilic as well as that of the hydrophobic groups, which makes them um, to be used as an insulator, uh, as well as that as a adhesive. So that's all about this biopolymers. Next, moving on towards the states of polymers. So polymers, so as such, if you see in case of the solid state chemistry, you basically have two types of systems. So one is your amorphous and another one is your crystalline. So amorphous systems are the ones which basically do not have any long range ordering of the atoms, as well as there is no periodic arrangement of the cells. Whereas in case of, so in all these crystal structures, okay wait, so amorphous systems, there is no long range order as well as there is no periodic arrangement of the atoms. Whereas if you see in case of the crystalline materials, there is both long range order as well as that of the periodicity exists in the crystalline materials. So in case of the polymer systems, we have two different varieties. Uh, we predominantly speak about amorphous systems and semi-crystalline systems. So semi-crystalline as in a combination of both amorphous nature as well as crystalline nature. So we do not specifically speak about crystalline polymers, or you can say 100% crystallinity in case of the polymers is not achievable. So any so can anyone tell me why this 100% crystallinity in polymer is not feasible? Amorphous systems is typically more of a disordered state where your uh, polymer chains, or you can say the macromolecules which is there in the melt form, will be in a more disordered state. Whereas when you cool, or when you basically bring these polymers into a solid state, they will be more of in a partially ordered state. You cannot say completely ordered state, but they will be in a more partially ordered state, and that's what makes it semi-crystalline. But 100% crystallinity achievement in case of polymers is difficult. So any rough understanding of why is this 100% crystallinity is not feasible?
Because polymers are like very strong thing.
Hmm. So these as she kind of rightly said, macromolecules are more in a haphazard manner, so they are entangled in nature, so they are basically folded. So when you cool them, what happens is, or when you try to solidify them, what happens is that the entanglements cannot be folded in many conditions. So because of this, and also due to this kinetic limitation, and since the rate of crystallization is limited, the kinetic limitation also plays a major role in this crystallization process of this polymers, because of which 100% crystallinity is not feasible in this case. So talking of crystallinity, if you see, there are so you basically have a unit cell. These unit cells are kind of a building block for this crystalline materials or crystalline systems. So these unit cell basically repeat itself to form a crystals. So there are two types of crystal systems. One you can say is the single crystal, so which typically has similar crystal structures throughout its system or throughout the material, and another one is basically your polycrystalline materials. So polycrystalline materials as such, what we actually mean is that they have different crystal domains, and each crystal domain basically has small crystals called grains, and these grains are typically separated by something, by a boundary called grain boundary. So this crystallization, as we speak about in case of the polymers, or you can say the solid state macromolecular systems, can be attained by two different ways. One is basically you try to cool down the system. Second thing is by solvent evaporation. So these are the two ways in which you can actually form the solid state of the macromolecular systems from its liquid state. So the crystals usually here of the macromolecules are of two different types. One is what you have as a extended chain crystal. So once you lower down the temperature or try to do this solvent evaporation, these entangled or basically the coiled, um, I would say entangled macromolecules tend to align along the or tend to extend, and thereby it forms a extended chain crystals. But because of this kinetics and rate of crystallization and the entanglements already present in this polymer chains, the folded chain crystals are something that is more common. So two types, one is extended chain crystal and the second type is folded chain crystal. So the most common among these two is the folded chain crystals. The major reason is basically because of the entanglements present in the polymer chain, which try to keep the crystals in a folded shape. So as such, when you say extended, all of them will be aligned with respect to one another. Whereas in case of the folded chains, there will be the folds within this. There will be the folds which will form the crystals. So there are variety of methods as we discussed right now, that for one of these method is to basically cool down, and another one is basically to quench, and another one is basically to do kind of some sort of a solvent evaporation. So depending upon these kind of techniques that is used for this crystallization, varieties of crystal is formed, because the condition in which you actually do this processing influences the crystallization process. Well, this is something very typical. The crystallization, what crystals you form at the end, depends upon how you are processing or how the system is being processed. So depending upon the conditions of the crystallization, your um, crystallinity will change. The crystallinity as well as the type of the crystals formed out of these polymers will change. So, when does this crystal systems, or if you have to see whether a polymer is crystalline or amorphous. So, as we said, there are two varieties of polymers. One is basically the amorphous nature, and then the other one is the semi-crystalline. So, one way to actually see the whether a particular polymer is semi-crystalline or amorphous is using this X-ray diffraction uh, characterization technique. So by the diffraction of these X-rays which falls on your sample, you will be able to tell the percentage of crystallinity that exists within your polymer samples that you are taking under consideration. So in case of an amorphous systems, what you would typically observe is that there will be a broad peak, a broad X-ray diffraction peak will be observed. Whereas in case of the crystalline materials, it will be more of a sharp peaks. So that's the characteristic difference. So based on the type of peaks that you get through these X-ray diffraction, we qualitatively as well as quantitatively we can describe the percentage crystallinity present in the system, as well as whether the sample is totally amorphous or it is semi-crystalline in nature. The second way to do is through the differential scanning calorimetry technique. So over there, based on the enthalpy of melting and enthalpy of crystallization or fusion, you can determine the percentage of crystallinity in your polymer sample. So we have so we right now we know that polymers can be amorphous or polymers can be semi-crystalline. But actually, what determines this crystallinity and this amorphous nature is basically the answer to this lies in the molecular structure of these polymers. So, if you are given a polymer and if you are asked to judge or basically explain whether it is a crystalline or whether it's a semi-crystalline or amorphous, then we need to have certain judging criteria to to explain or to basically or to evaluate whether this polymer is amorphous or semi-crystalline. So obviously, it is not possible for us to remember. So there are lot of polymers. It is not actually possible for us to remember. I mean, hardly we will be at any point of time, if asked, we will be able to remember about 15 to 20 or at the max about 30 polymers names. So knowing their properties will be extremely very difficult. But through certain judging criterias, we can actually tell, or we can qualitatively say whether this is whether this polymer is going to exhibit this kind of behavior or not compared to other polymers. So these polymers can exhibit these properties compared to the other polymers. We can have a qualitative judging using few simple criterias. So to um, see whether a polymer is amorphous or crystalline, you can see for their bulky groups that is present in the polymer. So if the polymer contains a lot of bulky groups like styrene specifically, it's a very bulky group which you have in the polymer, uh, which you have in the polystyrene polymer. So these bulky groups, what they do is they try to contribute a lot of steric inherence to this polymer backbone. So since, as we discussed, that folded chain crystal is most commonly observed, so folding is not much possible in this case. So that is the reason your polystyrene molecules will, so folding is very difficult because of the stirring hindrance these uh, bulky groups actually contribute to. So due to this, the polystyrene is amorphous polymer. So this is one wherein the bulky groups basically provide a lot of steric hindrance. Next one is the cross linking. So if your polymer system that you're going to or if the polymer system which is given to you has a lot of cross linking, so then also this folding will be very difficult because of the rigid interlocking between the due to the rigid interlocking of the bonds. This folding will be very difficult, and that is another reason why these polymers or the cross-linked polymers are typically amorphous in nature. And then in case of copolymers as well as blends, also this is not possible to crystallize, typically because of the differences that comes with both the monomers that you are taking under consideration, or both the polymers that you are taking under consideration, due to the difference in the properties, physical properties, as well as some of the chemical properties of the two polymers or two monomers that you take for forming copolymers or blends. This crystallinity is compromised. So these are three criterias. Well, there may be more, but for as far as the scope of this course is concerned, we will stick to these three criterias. So after this, we basically deal with the more of the thermodynamics of the crystallization process, where we will see about more about how this crystallization kinetics works and their thermodynamics works. And you can say that we will also go through few of the properties of the crystal systems, like the size of the crystals, and then the effect of diluents, and kinetics of the crystallization systems. So um, typically speaking, the crystallization, if you see, is nothing but you move from the liquid state to the solid state, and this is a first order phase transition. So there is basically a phase transition from the liquid to the solid. A phase is changed, and this phase change is a first order transition. And the typical reason why it's a first order transition is because the second derivative of this Gibbs free energy or the entropy is a discontinuous curve. So This crystallization or melting, you can say, is a first order transition. So typically, if you see in case of crystalline materials or yeah, in case of crystalline materials, if you see the point at which it moves from solid to liquid and the temperature at which it moves from liquid to solid, both will be the same. Uh, Liquid to solid and solid to liquid. Both melting and crystallization point will be the same. However, in case of the macromolecules, this is not true. Both the crystallization temperature and melting temperature vary up to 10 to 20 degrees Celsius. Any idea on why is it so? And there is also another one, you can say, interesting um, some sort of an observation is that in some polymers, not all, but in some polymers, once the polymer gets melted or once you basically raise the temperature for these polymers above their melting point, they do not actually come back to its crystalline state when you cool it. So you when you heat them, they basically exhibit a melting peak. I mean, so they basically exhibit a melting temperature. But once you heat, uh, they basically exhibit a melting temperature. But when you cool them, they do not exhibit any crystallization temperature. Crystallization point was missing. So this is also one of the kind of observation. Specifically, this case is more common in conducting polymers where we observe for a melting point. But if you see, I mean, I'm talking with respect to the differential scanning calorimetry. But when you actually try to cool down the system, you don't see a crystal. You don't see a crystallization point. So the question now for our discussion is that the crystallization temperature and the melting point in case of the macromolecular system or polymers are not the same. They both are different and they vary up to 10 to 20 degrees Celsius. But whereas in case if you see for these common crystal systems, both these points are typically the same or they are very close to one another. Any specific reason of why is it so? Any idea on why is it? Let me mention this as a question. Yes. Hmm. 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 So you say that there is a time lag, right? So it can also be like that. Okay, but what is there any okay time lag? Any other answers? Hmm. Hmm. Okay. Okay, so we have two answers. Let me keep this question as such for the time being. So I request everyone to actually go and then look up on what all can be the possible reasons you guys can think, and let's discuss this sometime, in the next class, because this is a very this is quite important, and it is better to put some thoughts in this, understanding why there is a difference before we start discussing it among us. So please uh, go through this, and you can always check it out about why there is this difference between difference of crystallization and melting point in case of polymer systems, whereas that same does not exist for crystalline nature, for the other crystalline materials that those are present or those are available. Of course, we will surely discuss this one in the next session. Interactions, if you see, they are typically non-covalent in nature, and they depend upon the type of functional groups that are present in the systems. So, what are the type of non-covalent interactions you can actually think about in case of macromolecules? In case of macromolecules, yes, what different types of interaction? Mm. Mm. Ion dipole interactions, and hydrogen bonding, van der Waals forces, and what else? Van der Waals forces, dipole, ion dipole, hydrogen bonding. Yeah, so these are the typical examples. And for describing these kind of interactions, we have totally three different models. One is your hard sphere, and another one is your square well, and another one is the Leonard Jones. So they typically explain to us about the energy as well as the I mean, when you basically bring two um what do you say, two atoms near to each other, how does the energy, the potential energy between these two molecules is going to vary. So if you see in case of hard spheres, initially when they are far apart, there is no interactions as such within them, and when they touch each other, there is some sort of a interactions, and those interactions are typically repulsive. Whereas in case of square well, if you see, there are some attractive forces which is present in them, and in the Leonard Jones, if you see the curve, that up to a particular point there will be no infraction, and then there will be attractive, and once you come very close, there will be more amount of these repulsive interactions. So these three models basically explain us at what kind of distance what kind of interactions will be present within the atoms, or you can say atoms, that would be the best. So beyond this, we have something related to the discussion of glass transition. But since next week also the very first session is on glass transition, I believe it would be good if we take it as a stretch. So that is the reason that part is not yet, I am not going to cover in this live interaction session. However, it's the part of the week 3, the last lecture, glass transition. So today's this what do you say, conceptual this thing ends here. We have totally 11 questions to discuss in total, in all. So let's start with that. So let's go with the first question. Before that, okay, let's first finish these three questions before we move to the next one. Melting phenomena in semi-crystalline polymers is the zeroth order phase transition, first order phase transition, second order phase transition, third order phase transition. So all these questions that we are discussing are gate questions. So this is a gate question. I will write all the specifics of which years these questions were asked when I am uploading the slides, but these are gate questions. So now we saw, right, crystallization is what order of phase transition. Melting, yeah, first order phase transition. But how many? Okay, that is fine that it's a first order phase transition, but how many of us here actually have an understanding of what is this zero order, second order, or a third order phase transition, and any examples? Yeah, this is a first order phase transition, that is right. Because crystallization is first order, so melting is also a first order. But what about zeroth order phase transition, second order phase transition, third order phase transition? Oh, okay. The thing is, because no, it's if you start talking about this, then it will be like it will totally take. I mean, the main reason why I asked this question was basically because to ask you guys to go back and look at and then come. This we will not be touching up today. This will be shifting to the next session for sure. But I want everyone to actually go and look at what are the typical kind of phase transition that exist in the what do you say, in literature. I mean, whatever a phase, types of phase transition, because this phase transition as such, if you go and check, there will be a lot of theories related to this phase transition. How does this phase transition happens, phase diagrams, so many things will come up. Our goal is to basically understand what are these four orders of phase transition and how these orders are different from one another, and some examples of each. Let us discuss. So next one, glass transition temperature of a polymer can be determined by, actually if you see this polymer course, if you see many places, it would be like we actually need to go and look around the concepts in the internet. If you see, in many cases, even in confirmations, if you see, there are lots of terms like end to end. I mean, the whatever we discussed was very brief. Whatever that is discussed in the course is a very brief overview of polymer conformations. If you go in deep, then we will be discussing about a lot more on that. So this course is, if you see the lectures, these are in that way only. So where we actually need to go and look at the internet and learn a lot more than what is actually necessary. I mean, so it will help us. in a lot more ways. So, question 2, glass transition temperature of a polymer can be determined by which of the following characterization technique? Thermogravimetric analysis, differential scanning calorimetry, X-ray diffraction, and infrared spectroscopy. So, before, okay, so anyone, uh, can you please define or can you please explain what is glass transition temperature? I mean, it's a part of the week 4, week 3, what do you say? It's a part of the week 3 lectures. So, I mean, what temperature is this glass transition of a polymer actually means? What does a glass transition? It's a transition, and this basically happening at a temperature for the polymers. But what is this? What actually happens? Mm, I mean, the first part is right. The glass transition is basically the temperature in which a polymer moves from the glassy state to the rubbery state. The second part, it moves from the viscoelastic, that is correct. Now, does it move from. Okay, so I will think about this and then I'll come back. So, what about these other characterization technique? Any idea on what is TG? I mean, the thermogravimetric analysis, X-ray diffraction, or infrared spectroscopy? Hmm. 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 Infrared spectroscopy uses infrared IR rays to determine the functional group present in the sample. So typically we call this as Fourier transform infrared spectroscopy because the signals that you get is actually kind of Fourier transformed. So that's a mathematical function which it gets Fourier transform, and then we get it in the form of a plot of transmit of absorbance of these uh, IRAs versus the wave number, and depending upon the positions of the peak what you get, we can identify what kind of functional groups is present in the system. Similar to infrared spectroscopy, you have X-ray diffraction, so are uh, wherein these X-rays hit the sample, and depending upon the crystalline domains, depending upon the planes that is present in the system, it gets diffracted. That diffracted X-rays are basically captured by a goniometer, and depending upon that, we actually get whether the crystallinity and then the crystallinity percentage. Thermogravimetric analysis is more of how does your it basically deals more with the thermal transition that happens in the sample. So depending upon the weight loss at each stage, so what you do is you basically take some amount of the sample and you heat the sample from let's say room temperature to a very high temperature of 608 or 800 degrees Celsius, and then you observe the weight loss. Depending upon the weight loss, you can actually correlate that to the different type of thermal transition that happens within the sample that you are going to analyze. So, I mean, this is just a very small, I would say, like very brief about these characterization techniques, but all these fours are predominantly very important when you are doing material characterization. So if you guys are interested, or if you are into that field of materials, or if you want to go, then it is better then having the fundamental understanding and then the fundamental working principle on these types of material characterization techniques, I mean basic material characterization techniques, will be very useful. So, third, quenching of the polymer melt leads to question number three. Quenching, I mean, okay, this we haven't discussed in the while. But again, this is a part of the week three course lectures. So, okay, what is the meaning of quenching? Quenching. No, it's something related to cooling of the system. So quenching means sudden cooling, like you cool the system abruptly. You take it from whatever temperature from the initial state of that system to to a lower temperature, and this decrease in the temperature is not going to be gradual, but it is going to be sudden. That is what is quenching. So quenching is more of these metallurgy terms. They tend to use this words quenching, annealing more often in metallurgy and material science. So quenching means sudden cooling. You basically cool the system not gradually but more abruptly. So does it basically result in crystalline polymers? Of course, that is not going to happen. As we said, 100% crystallinity is not going to be possible. Or is it going to be amorphous? Or is it going to be semi crystalline? Or is it going to be a combination of, you can say, okay, a combination of all. I think it's better to write this as none of the above. This is not a question taken from anywhere. This was made by my, I mean, by us itself. So, I mean, the answer is going to be either between B or C. It is amorphous, and any reason? Hmm. 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 So the polymer chains has entanglements, right? The macromolecules will be entangled. So once you do sudden cooling, as you said, that there won't be, if the process is not going to be gradual, these entanglements cannot align themselves in that particular fashion. It cannot be, it cannot fold itself. So due to that only, this quenching is because of that reason only, this quenching of this polymer actually leads to amorphous solid and not a semi crystalline one. So before moving on to this, last class we discussed about a question, but I'm not sure how many of you were present or how many of you, I mean, saw through that recorded lecture. But question number 2, it was a kind of a tedious as well as a fun task, but I'm not sure how many had tried it, but again you can see this. So the structure of a cross-linked polymer is given. So this is a combination of two monomers, typically condensation polymerization. So you are asked to identify the monomers that are used in the synthesis of this polymer, what you can see in this picture. So I gave two clues. One was a condensation polymerization between the two monomers, and one among the two was melamine. So melamine typically has a structure of NH and then this ring with three nitrogen atom, this hetero atom ring, and again these NH on the either sides. Like if you take this as the ring, to in 1 2 and 1 3 and 5 position, the NH groups will be attached. So that is the structure of melamine. So what should I basically, what is the other monomer that I need to react this melamine with, or what you can say, melamine should react with what other monomers or undergo condensation polymerization to form this polymer structure that you can see in this figure. It's a condensation polymerization. If you haven't tried, then we can go back to the lesson. Again, it's a gate question, gate 2023. I mean, there were options, but here I purposefully I removed the option so that it can be like a kind of a to make the things slightly more difficult. I just uh, removed all the options so that I wanted people to play around with this different types of monomers and then check out what kind of polymers will be formed and match that formed polymer with the question and then see whether the answers are matching. So for this question, I will update in the already uploaded PPT so that people can see. Or again, if you didn't attend the previous session, then you're always welcome to see this question right now and then try on yourself before I update that PPT for week 2. So, so before going to this one, let's go to question number 12. This was something related to week 1 and week 2, but it's fine. Polyamide 66. I hope now everybody would know what is polyamide 66 is. It's nothing but nylon 66. This is prepared by condensation polymerization of 0.08 mole of hexamethylene diamine, 0.08 mole of adipic acid, two monomers. Now the polymerization reaction is happening and then you are going to get the reaction product, but then the reaction product here, the reaction is not going to be 100% what do you say, the conversion efficiency is not going to be 100%, but you have 0.002 mole of unreacted carboxylic acid groups. You have that the molecular weight of the repeat unit of the polyamide 66 as 226 gram per mole. They are asking you to calculate the number average molecular weight of the nylon 66 in the reaction product. I think this is something very similar to the question that we did in week 2, the second problem. I mean, there the question was to, if I'm not wrong, it was to there we were given the number average molecular weight and the weight of the repeating unit, and then we were asked to calculate the conversion efficiency. I hope everybody remembers this one. Yeah, this question. So here we were asked to calculate the conversion efficiency, and then we were given the number average molecular weight. We were asked to calculate the molecular weight of the repeating unit by ourselves, and then after that we were asked to calculate the conversion of the monomer in terms of percentage. Here it's the other way around. I have I have given the conversion efficiency, but in indirect ways. Molecular weight of the repeat unit is given. You just need to calculate the number average molecular weight. So how do you proceed, and what, I mean, since we did that, this should not be that difficult. So what will be the answer? This is supposed to be easy. I mean, so what is the value of P? P is nothing but it's the conversion percentage or the formula. The formula, actually, I mean, if you know the formula, then everything again is as simple as the one that we did last week. Can we say this as number of functional groups reacted to the number of functional group present? Yes, I mean, is this formula fine? Oh, functional groups, sorry. So, the functional group reacted as such is nothing but the functional group already present minus the functional group. Wait, just wait. Number of functional groups reacted is nothing but it's equal to number of functional groups uh, present minus number of functional group. Instead of saying present, you can say present initially unreacted. Can we say this way? So what will be then the number of functional group reacted? You can say this in terms of the moles itself, right? So present initially was zero point zero 0.08 plus 0.08 minus the functional groups that is going to go unreacted is nothing but the carboxylic acid group with the mole with the 0.002 moles. So minus 0.002. So this is going to be 0.16 minus 0.002. So which will be nothing but how much is it? So 0.16 minus 0.002. Sorry, 0.158, and the present initially will be 0.16. So P is nothing but, can we write it as 0.158 by 0.16? So what is that going to be? Sorry, 0.16, 0.9875. Is this fine? The extent of reaction P, this P, I think, I mean, this was discussed in the course, so you can also look at this here. So once you know this extent of reaction P, you can calculate dP as nothing but 1 by 1 minus P. So which is nothing but it's going to be 1 by 1 minus 0.9875. So let's use the calculator. 1 minus 0.9875 is 0.0125. So 1.0125 is going to be 80. So degree of polymerization is 80. If you multiply this with the molecular weight of the repeating unit, what you will get is the number average molecular weight. Yeah, 2 to 6. So what will be the, I mean, is that this thing is correct, or is there any? So yes, I mean, any answers? Similar answers or other answers? 18080 gram per mole. I might be wrong in any calculation. So if you find any mistakes, then please let me know. Okay, so I will leave this question here. If you find anything, what do you say, wrong, or if you have any clarification, then you can ask, or otherwise we can go to the questions which are dedicated for today. Question number 4. Viscosity measurements were performed on set of PMMA solutions at different concentrations in toluene at 25 degrees Celsius. Oh, plot of reduced viscosity against the concentration produced an intercept of 21 on ordinate c equals 0. So if you basically plot a curve between the reduced viscosity and the concentration, whatever the curve that you are going to get is going to cut the y-axis at c equals to 0. The value is going to be 21 cc per gram. The value of the viscosity reduced average molecular weight in toluene at 25 degrees Celsius is. and the given data is the Mark-Houwink constants K and A, that is 7.5 into 10 power minus 3 centimeter cube per gram, and A values 0.72 for PMMA in toluene at 25 degrees Celsius. So these values are what do you say, they are specific. So they are specific for a polymer solvent system, so these values cannot be changed, they are actually taken, and they are specific to this PMMA in toluene at 25 degrees Celsius. If the temperature or the solvent is varied, then these values can change. How to go about solving this equation? There is a hint, it's the Mark-Houwink constants are given, so it's about using this Mark-Houwink equation. So you have the value of K, you have the value of A, you are supposed to calculate M, and you have viscosity also. So what would be the answer? I think it's going to be very simple. It's just that you need to put it in the equation. But so what would be the equation? Let me put it. Do we have? Okay, that's fine. So the formula is intrinsic viscosity is equal to K times M, that is your molecular weight, average molecular weight, to the power A. So intrinsic viscosity is equal to K, which is your constant, times molecular weight to the power A. A is again your constant. As I said, it is specific for a particular polymer solvent system at a particular temperature. Now you are given reduced viscosity. Again, as far as the viscosity is concerned, there are different types of viscosity. So here what you have is a reduced viscosity, but we know that the reduced viscosity has a, I mean the plot of reduced viscosity against concentration has an intercept of 21 cc per g at a ordinate c equals to 0. So based on this data you are supposed to calculate. So this let me just put this in the, so can you see this different type of viscosity table, or should I need to make it a bit more bigger? Mm. Mm. So I hope it is visible. So do you see on the left hand side we have different type of viscosity, like a relative viscosity, specific viscosity, inherent viscosity, reduced viscosity, intrinsic viscosity, absolute viscosity, and kinematic viscosity. So I hope everybody will be more aware of the absolute viscosity and kinematic viscosity, especially the mechanical as well as chemical engineers. So other than this, these are other few types of viscosity which is available, which is they I mean other type of viscosity which we use to describe the describe different systems. So if you see here, your reduced viscosity is nothing but specific viscosity by concentration. So specific viscosity is nothing but it is absolute viscosity minus your N naught. Uh, I should be more. Just a second. N naught. Hmm. So the eta is your absolute viscosity of the solution minus eta naught is the absolute viscosity of the solvent. So eta minus eta naught by eta naught is nothing but is your specific viscosity. Specific viscosity by the concentration of the polymer solution is going to be a reduced viscosity, and when this reduced viscosity at a concentration C tending to 0, the reduced viscosity can be called as the intrinsic viscosity. So that is what is we have it here. So you have your reduced viscosity, but at C equal to 0, that reduced viscosity value is 21 cc per g. So here intrinsic viscosity is nothing, this value is going to be your intrinsic viscosity. So let me write it here. Reduced viscosity at C tending to 0, or in this case equal to 0, that's fine. Oh, whatever. Tending to 0 implies that this viscosity is nothing but it is the intrinsic viscosity. So again, what is reduced viscosity? Reduced viscosity is nothing but specific viscosity upon concentration of the polymer solution that you are taking. And what is the specific viscosity? It is nothing but viscosity of the solute to the viscosity of the solvent. So in case of a polymer solvent system like PMMA and toluene, it is specific viscosity is nothing but the viscosity of PMMA by the viscosity of the toluene, and so reduced viscosity will be nothing but specific viscosity by concentration of the polymer solution, and when this concentration tends to 0, that reduced viscosity is called as the intrinsic viscosity. Here what we have is that we at C equal to 0, reduced viscosity is 21. So that means it is the intrinsic viscosity. So intrinsic viscosity is 21 cc per g, and K value is 7.5 into 10 to the power minus 3. I am just going to copy paste, times your M, that is the average molecular weight which you are supposed to find out, to the whole power A. A is 0.72, which is given. So what is the value of M? To make it more clear, I am adding extra brackets. Answer, I mean, it's just about mathematics right now. So what is 21? 2800. 1 and 2. Is this fine? It makes sense. Then it's just about again another one round of 1.38. Just a second. Wait, I think there's a mistake. Oh, okay. So it is 2800 to the power 1.388. So you can take it as 389 for, or you can keep it as 3. Yeah, it is fine. It's better to take 389. Is M. So what would that be? 2800 to the power 1.389. It will be somewhere around 61,390.688 gram per mole. This should be gram per mole. Or if you take it as 1.388, then it would be 60,000. 1.388, then the value will be around 60,905.336 gram per. No. Any questions? No. Anything to ask, because we haven't discussed any sort of question like that till now. So if you have any doubts, then let me know, because we have a similar question again here. But here it is just that I have given the relative viscosity. So once you have this relative viscosity, you are supposed to calculate the what do you say, intrinsic viscosity, and then you just need to, again the same thing, substitute. So I will leave this. You guys can take it out as a this, as a, practice question, and then solve it, and then do let me know if there is any what do you say, difficulty. So let's, I'm not going to solve this for this class. because I have shown one sort of an example here, so I expect you guys to actually take this question. You can take a snapshot right now, or when I upload you can take this question and then solve, and we will discuss this in the next class. Like, we can also have some sort of a recap of the things that we learned. That is the reason I specifically took this question, because we will have some sort of a recap to what we have actually learned in week 1 and week 2. So it's a 12-week course. So what we will be learning in the 11th or 12th week, we may, hopefully we should not, but sometimes we may forget some of these formulas, and it might be difficult for those, especially who are going to appear for exam after the course. So that is the reason I plan, I mean, I wish to always keep one question, one or two question of the previous session in this one, so that we can have some sort of a recap. So this we will do it next week. Now let's go to question number 6. PVDF was quenched from the melt in one case, and in other case it was cooled from the melt at 10 degrees Celsius per minute. The percentage crystallinity of the slowly cooled PVDF is 60%, whereas the heat of fusion for the quenched PVDF is. Before doing this, can we do something more simpler? Yeah, let's first do the question number 7. The enthalpy of a fusion for a polymer is found to decrease from 135.6 joule per gram to 120 joule per gram after 5 years of use. If the enthalpy of the fusion of the same polymer with 100% crystallinity is 290 joules per gram, then the loss in the crystallinity after 5 years. So you have a polymer, you know the enthalpy of fusion is 135.6 initially, and you know that it has a crystallinity of 290. It has a enthalpy of fusion with, when the polymer is having 100% crystallinity, the enthalpy of fusion of that same polymer is 290. So what it actually means is that the polymer what you are having with you is not 100% crystalline, because the enthalpy is less, so crystallinity will be reduced. After 5 years from now, you are again going to take the same polymer, and then you are going to run some sort of a characterization technique to, and then you find out that the enthalpy of that fusion after 5 years is 120 joule per gram. So over the period of time, the polymer has aged, and because of that aging, the crystallinity in the polymer is lost. So obviously any material that you take, it ages. So as it ages, it tends to, the properties tends to vary. Majority of the cases, the property will degrade as you progress with time. So that's what is also depicted here. The crystallinity has reduced because the enthalpy of fusion value has decreased. So we are asked to calculate the loss in the crystallinity after that 5 years time period. So enthalpy of a fusion is more of a characteristics of the crystallinity. So higher the, higher the crystallinity, the enthalpy of fusion will be more. So since this enthalpy of fusion here is decreasing, what it actually means is that the crystallinity is going to be reduced. Thankfully here the question says that loss in the crystallinity, but it should be well understood that when enthalpies of fusion is decreasing, which means that crystallinity is reduced in the system after the period of use. So how are we supposed to calculate this? It's a very simple relationship. You just need to think from the perspective of three things you need to consider. One thing is fusion, at that present time with 100% crystallinity and percentage of crystallinity. If you use these three parameters, you can solve this question very easily. Yes, I mean, any idea then come to your mind while seeing this question, or how to solve? And what is your delta HF? Xc is your crystallinity, right? And delta HF is, no, I mean, what do you actually mean by delta HF and delta HFC? Hmm. Okay, so then how you will, I mean, how am I, so what will be the equation then? Heat of, hmm, hmm. So, oh, hmm. Now, you so with respect to this question, your delta HFC is what? What is the value? 135.6 or 290? Not the initial, but then that same polymer, but if it has 100% crystallinity. Initial one is 135.6. 290 is if you have the same polymer, but let's say that polymer is going to have a crystallinity 100 percentage. Let's say I make it somehow 100% crystalline, then at that case it is going to be 290. So can you write something like this, whatever that mm, X in one case is um, you cannot tell like that, because in both these cases, either now or after 5 years, Xc is not going to be 100 anywhere. It, because you see, if you have 100% crystallinity, the value is 290, but if you see initially it is only 135.6. So enthalpy is lesser compared to what it should have if it was 100% crystalline. So it actually means that the polymer that I'm currently having does not have 100% crystallinity, but something lesser than that. So this enthalpy of fusion of the same polymer with 100% crystallinity is something that is derived from the literature. It's like, see, we described, right, that polymers cannot have 100% crystallinity. So it's something like more of a, you can say, like kind of like extrapolating the curve. If this was this value at this particular what do you say, at this particular crystallinity, then what it could have been at 100% crystallinity. So then in that case, enthalpy of fusion of that polymer, is equal to, can I write this way, enthalpy of fusion of the same polymer, just a second, times of the same polymer at 100 percentage crystallinity times percentage of crystallinity. Screen is not visible, just a second. Okay, okay, just a second, let me stop presenting. And is it now visible? I mean, can you see it? Okay, okay. So can I write it this way? If you want, you can. I'll put it in number persons. Oh, I mean, does this equation make sense? Okay. Is there network connectivity issue from my side? I mean, is screen visible? So, I mean, does this equation make sense now or anything? Hmm. 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 Okay. Hmm. Ah. Hmm. And that times the percentage of crystallinity will give you that one that you have currently right now. So can it be written now like this, 135.6 joule per gram equals to 290 joule per gram times percentage crystallinity. I mean, when I said percentage crystallinity, you'll get it as a fraction. Let me just write it as crystallinity itself. Is it okay right now? Okay. So what would be this crystallinity at that particular like the current one? What it would be 135.6 by 290. So that would be 135.6 by 290. 0.467, or you can say 46.7 percentage. Oh, sorry, 46.7. Similarly, now after 5 years, as I said, the material has undergone some sort of a change. Typically in polymer case, we say it has undergone some sort of a degradation. So due to that, the enthalpy of that fusion of that polymer at that time is reduced. Let's say it was subjected to some sort of a service, and whatever, we don't care about the history of that particular 5 years of time. So what we have is that it has now reduced to 120. So because of which, since as I said, enthalpy of fusion is decreasing, which means that the crystallinity is reduced. So now what will be the crystallinity in the polymer? Can I write it as 120 by 290? Again, here it does not mean that we change the equation to enthalpy of fusion of the polymer at the present condition. Here also we are seeing what would be the percentage crystallinity after 5 years. So here also this delta HFC should be into the equation. So this equation will remain same irrespective of the time periods you are considering for the calculation. So 112 by 29, 41.37 or 0.4317, or you can write it as 43.17 percentage. Now we are asked to calculate what is the loss in the crystallinity. So they are asking the percentage lost. So what is the difference that they are asking? So if we subtract both crystallinity of polymer sample after 5 years minus crystallinity in polymer uh, before, or I can say at the starting, or at initial condition, at initial condition is nothing but loss of crystallinity in the polymer. I mean, does this, is this fine or any? It's just that I need to, I mean, since this is a loss, it should be initial minus final. Or otherwise, you'll get the answer in terms of negative. But since we are asking for the loss, you should, it is well understood that the negative sign means the loss. So, answer should be represented in the positive value. Absolute value of the answer should be written. So that is 46.7 minus 43.17. So what is that value? 5 point something? Okay. Hmm. Just a second, 1 minute. Oh, sorry. This is 41.37. You can calculate. 12 by 29 is 41.379. So if we take 46.7 minus 41.37, then it is somewhere around 5.33 percentage. This is the loss in the crystallinity if the system undergoes, I mean, after 5 years of the system's use, 5.3 percentage of its crystallinity is lost. So I hope there is, if you have any questions, you are welcome to ask regarding this, or we will solve one more question probably today before we wind up our session. We actually planned for around 11 questions, I mean, together with the MCQs. There is a very similar question like this, question number 6. So again, I am going to leave this question for the time being, but this will be uploaded in the uh, you know PPT, the presentation that I will upload it later in the coming week. So you guys can go and solve this question, and I hope there should be not much of a trouble. But again, if there is any questions, then you are always welcome to ask. Either in the live interaction session, or my mail ID will be given. You are always welcome to email me. I will respond to you as and when it is possible. So then let's see this question. It would be a pretty different way of questioning because it involves density. So, but anyway, let's see. There are two different PTFE specimen. I hope everyone knows what is PTFE. Ethylene. Other than this, the common commercial name? No, that's the use, right? So, commercial name of the polymer. Okay, fine, you can always look at it. The PTFE1 has a density of 2.144 gram per cc and its crystallinity is 50%. 50 percentage. The PTFE2 has a density of 2.215 gram per cc, but its crystallinity is 75 percentage. Now you are asked to assume that the polymers are pure and defect free and calculate the density of pure 100% amorphous specimen. Here you need to think that the polymer density is going to be a combination of density of the is going to be a combination of the um, crystalline domain density plus the amorphous domain density. So consider your polymer has both because it's a semi-crystalline nature system. So it has basically crystal domain as well as amorphous domain. And then you need to take the contribution from either of these to find the overall density of the sample or of the specimen as mentioned here. Try to think from the perspective of representing the overall density of the sample as the density of the crystalline domain and amorphous domains. Again, those densities will be different. If you see, in case of amorphous domain and crystalline domains, densities will not be the same. And can anyone tell me why will the density of a crystalline domain and these amorphous domains will be different and not the same? Hmm. So, within a particular volume of the specimen, if you take under consideration both the crystalline and amorphous domain, within a particular volume, the amount of polymer chains in case of the crystalline domain will be more packed, as someone just said, compared to that of the amorphous domain. So, due to this, the crystalline domain will have a higher density compared to that of the amorphous domain. So, can you guys think about it and then come back, or shall I give the equation? I mean, once the equation for all these questions, once the equation is given, the mathematics is just about plugging in numbers. Then the rest is just basic arithmetics. Nah, you can come up. I mean, that's the reason I told you have to basically think about expressing the density of the specimen as a combination of the density of the crystalline domain and the amorphous domain. And of course, you need to consider their contribution also, because it's not that the system is 100% crystalline, right, to say that density of the specimen equal to the density of the crystalline domains that is present in the specimen. It has both the combinations, so you need to account for their contributions as well. So I'll just give the equation, because I mean, you guys can think of, can you write, um, I'll use this row. Density overall is, can I express it this way, is nothing but density of the crystal domains, I can write, or let's say crystal times uh, xc, that is your contribution from that fraction of crystallinity, plus density of the amorphous domain times 1 minus xc, 1 minus the fraction of the crystallinity. You can also express it as xa, but let me keep it as 1 minus xc. Does this make sense, this equation? So you are basically, as I said, it has both domains, crystalline domains times their contribution plus the amorphous domains plus their contribution. If you plug in x, the value of this crystallinity xc as 0 or 1, you can actually get. So if you say x, this xc as 1, then what it means is this row amorphous will become 0, this particular factor. So then it actually, what xc equals to 1 means that the entire system is crystalline. So row of the specimen is going to be row of the crystal domain, right? And if you take this xc value as 0, what it means is this factor will become 0 and 1 minus 0 is 1. So row overall will basically become row of the amorphous domain. So let me leave this question here. I mean, so that I request all of you to just look at this equation, and if you have anything to discuss, I mean anything which you are not able to uh, understand, then we will discuss this in the next class. We will start our next session after once we discuss the concept. We will start our discussion with this question. The very first problem that we will take on the week 4 live interaction session will be question number 8 of this session. So, any questions apart from that? And I'll just stop presenting. So, okay, just let me share my screen. Is this fine? Okay. So, yeah, one of the questions that you asked, right? So, glass transition, in which it moves, it is actually a kind of a transition from glassy state to rubbery state, and then again you said that it moves from viscous state to elastic state. Shouldn't it be the opposite? Shouldn't it be from elastic state to viscous state? Because once you're going to heat, what is going to happen is the polymer what you're going to take is going to more exhibit more of a flow like behavior, because the bonds what is um, connecting the, I mean what is there in the polymer, they are actually going to be more fragile because of the increased temperature and the increased thermal motion. So shouldn't it be from elastic state to viscous state? Yeah, 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 yeah. With solid it is elastic, right? uh, Hmm. So that's the reason it is better to remember one thing is glassy state to rubbery state, and another thing is, since you actually brought in this elastic and viscous, it is also better to have the remember glass transition temperature also as the temperature at which the polymer starts exhibiting a flow like behavior. So that would be like an extra, what you can say, uh, explanation what you can give for this glass transition temperature. So yeah, thank you for asking that question. Okay. So if you have anything to discuss, then please go ahead, or otherwise we can conclude our session for today. Yeah, yeah, yeah. Go ahead. Hmm. 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 No, actually, I'm not exactly very sure. No, because I'm not 100% sure. I have some idea, but I don't want to uh, tell here unless I have some concrete this thing on that. So probably I will just what I can do is I can either take up this in the next class, or when I upload the presentation I can just give a brief um, what do you say, a brief explanation for that. I mean, will that be fine with you? Hmm. Hmm. Well, talking of non-equilibrium states, then I have to check, because I think that will be a totally a different concept to discuss about non-equilibrium states of polymers. Again, I will just look through this, because relaxation forces I have some idea, but this non-equilibrium states I have not ever explored. So I will look through those, and then I mean, if it is, I mean, if I can combine this inside one slide, then I will do that, or I will take this in the next class, non-equilibrium states of polymers. Yeah. So, okay. So then, thank you let me conclude the session. So, thank you everyone for joining. This session is getting recorded and will be uploaded by the next week. So you guys can always mail me regarding your doubts. I will try to answer them as soon as possible. So then I would like to thank both Professor Abhijit Deshpande as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon. Our next session will be on 17th August from 5 p.m. to 7 p.m. for week 4. So till then, thank you. Have a wonderful weekend, and yeah, bye. Yeah, bye.